Welcome to this talk on complexity introduction. This is part of the Big History and Complexity workshop, which is run in conjunction with the Big History Conference. There'll be a number of talks later on complexity and big history. This talk is just to give a little bit on the background, some of the big history patterns seen previously, overview of some of the talks, and the objectives that we have for this workshop. So the background considers different aspects of complexity and different forms of complexity. Big history patterns considers some of the major identifications of patterns found in big history. There's be a number of talks, and we'll kind of break it down by the topics that are going to be considered, and then we'll look at some of the objectives, including publication and trying to form a discussion among researchers in big history. So first, just an overview of some complexity aspects. Seen on the right is a complex adaptive system model, and some of the aspects that we usually consider with complex adaptive system models are self-organization, they organize themselves. There's multiple levels in space and in size, each with multiple components themselves. There's interactions within and between the layers, and so they somehow maintain order through knowing the environment. So both environment internal and external, because they have to deal with the entropy generation. They need to stave that off so they can survive, and so they need to develop a model of the environment by learning, need to extract energy, and they need to reorganize when necessary. So some of the dynamics are that the complex adaptive systems need to adapt, grow, and reproduce, and evolve. And this is one model that is the panarchy model, and that is there are various phases as systems grow, exploit new parts of the environment. Eventually, limitations are reached within that environment. It then releases some of those materials when it can no longer grow in that area. It investigates the environment to find new resources, reorganizes to take advantage of those, and continues again in the same manner. And this occurs at the various levels or sizes of that. For example, at the society level, there are institutions, people, and within people, there are various cells, and so there are various ways and feedback mechanisms along this dynamics. So it's very rich kind of dynamics that go in complex adaptive systems. So here I show three different types of complexity. The typical ones are the ones that we see below. The first one is just the formation of particles. For example, here we show a molecule with atoms, and the atoms have nuclei and electrons. And so technically there's no energy flow in these systems, and so they would not really be considered to be complex. But they do have some virtual particle exchange in the quantum world, so they might be virtual complexity. And they do have different binding energy levels, which is very important when considering the dynamics, especially later when they interact to form complex systems. So another one is just complex physical systems, which are dissipative systems, which there's energy flow. Energy flow is used to maintain the system out of equilibrium. Shown here is a hurricane, which the temperature in the ocean enters the atmosphere and creates this pattern and continues it as long as that energy source is there. However, there's no agency. And so transitions are based on fluctuations, and there's no information and no internal models. So examples would be the sun, the hurricane, tornadoes, a boiling pot of oil. Then we have complex adaptive systems, which form various levels of life in terms of cells, ecosystems, human systems, and societies. And so there is still an active energy flow with agency now. So there's information gathering, processing, use, and learning. and learning on an individual and species level, for example, the evolution of these. And so we will talk about these different types of complexities. Let's go a little bit further into those last two. So complex physical systems, a lot of times you'll see a chaotic behavior, for example, the butterfly effect, where it's very difficult to predict very detailed scales, but you can predict large scale phenomena. For example, things will change. There's also bifurcations at certain moments when the limits are reached. There is a capability of the system to reorganize in more than one way. So it has to kind of explore the environment to figure out which way is better. There's also a lot of times self-similar fractals, for example, coastlines, snowflakes. There's also scaling and power laws, for example, in earthquakes, we see on the Richter scale. There's also self-organized criticality, for example, in a sand pile that Bach explored. Then there's also the complex adaptive systems, again, which is life. And so we have emergence and evolution, various networks in there. There's also specialty and also diversity in the interactions and various levels, for example, a hierarchy or panarchy. And there's also a large range of dynamics in there and coevolution both on a micro and macro scale. And so in terms of complex systems, the discipline has a variety of type of subsystems in there, networks, collective behavior, games, nonlinear dynamics, systems theory, pattern formation, and the one that we're very often involved with is evolution and adaptation. So there's been various history patterns seen throughout and being discovered in the connections, evolution, and development. Bjorgi Eksteg was one that really found this. Eric Heisen looked at the energy density flow. There's the size of big history objects. Jans looked at the macroscopic and microscopic trends. And also others in the late 1990s, Reeds, Press, and Carr kind of looked at the range of sizes and how they could be connected to fundamental physical constants. And then there's the acceleration of trends. For example, when Forrester looked at the population increase and found it was not just exponential, but super exponential or hyperbolic, and predicted that it would go to a very large number towards infinity in 2026, which is called the doomsday. Manfred Eigen, Nobel Prize winner in chemistry, but also evolutionary biologist, came up with a model that showed that evolution could form singularity trends. And Alexander Panov, who's involved with this workshop, looked at major events, and they can occur for every factor of 3 decrease in time. So just a quick view of these. These are the connections. Eksteg compared when some feature occurred in development of an individual and related to that when it evolved. So the first things that evolved occur earlier in time, and so they have the animal features, then the brain features, and then some abstract symbology features to it. And then Eric Kayson looked at the energy rate density and showed that over time it has been increasing through the cosmic development and then through life on Earth and society. There's also been different connections between the size of evolving systems and environment, for example, that form identified by Jans, and then also again in the late 1970s, looking at how the sizes of various big history objects depended upon just a few physical constants. And then the form of acceleration, show here the article from 1960 in Science behind von Forster and others that looked at the trend in the population, that it would come to doomsday on Friday, November 13, 2026. Of course, they knew that that was not going to be sustainable. Others have looked into it, and others, including Panov, have looked at event rates, and so that there is kind of a pattern involved with that. So in terms of the presentations here today, there'll be a set of them. The list that I have here is not by the sequence that will be shown today, but organized by some aspect of big history. So, for example, by the phase in time, cosmic evolution, chemical and life, human evolution, civilization evolution, and then potential extensions into the future. Then we also have a number of looks of various integrated frameworks. We have the look at complexity, big history, and education, and general concepts of complexity in big history. So be a number of these kind of scattered throughout the conference. And so we want to explore relationships to big history and connections to the previous work. And so often big history individuals have creative insights, and that's great. But we need to find what others have explored, and so we need to do transdisciplinary literature review, which is tough, kind of tie things together. So we don't want to herd cats. We don't want to have it very uniform. We want to have good discussion so we can connect together and connect what has been seen out there and connect what others are working on. So have good discussions, including that of what others have previously done. So the aim of the workshop is to refine these ideas, connect to others for suggestions, and further develop a research community, including publishing in a special issue of the Journal of Big History and then a monograph book similar to one in a Springer series. And to help, an online reference database was created and shared on Zotero. And a further tool might be publishing paper comments and responses in Journal Big History to have a continuing discussion of these particular topics. And so we have an example of building a case for singularity framework, and so it's based on kind of what people are very familiar with, the courses they might have taken in high school and college, and this forms kind of the phases, the cosmic and terrestrial phases of big history, just 4 of them, kind of astronomy, biology, human evolution, and world history. Then there's factors, for example, the cosmic age and terrestrial age is 3, and that was kind of identified by others also. And then the ratio based upon the terrestrial phase is about a factor of 1,000, with things occurring starting at 5 billion years ago, 5 million years ago, 5,000 years ago. And then we apply this geometric pattern to the next lower level. And then this was tied and informed by the research of many over a long period of time, including that of von Neumann, who kind of first recognized this type of trend in the late 40s, early 50s, and continuing on as people kind of develop this further. And so, in the conclusions of this is that complexity is important in big history and many other fields. So much has been done with it, and various things have been discovered already. There are many fascinating patterns, and so we should, kind of try to further that or test those or put those together. We would like to further explore this topic throughout the many aspects of big history, and you can see that the talks that we have today kind of take that view many different aspects, and objectives are to present, discuss, review, publish, comment, and develop a community. So often, sometimes we have to work together to kind of put the pieces of the puzzle together just to ask the right questions. And then once we ask the right questions, we can work further, find out what others people have said about that, and continue on from there. So I look forward to your participation. Remember to ask questions and think about what can be done further in this important area.